The next topic is another very interesting topic, actually, and we have a very eminent speaker with us who will be joining us. The topic is going to be improving deep tech research outcomes via access to global access, expert collaboration. And to share or to speak on this topic, we have Manish Gupta, who is the director with Google Research India. Uh, and Welcome, Manish.
Hi, Mangesh. Thanks for having me.
Am I audible? Hi.
Are you able to hear
Thanks
me?
for joining. Yes, yes, absolutely.
Okay. So, will you advance my slides, or am I able to do that?
I think you should be able to do that. I may not have control.
Okay. Okay. I'll do
Can
that.
you, if you are sharing your whole desktop, probably you should be able to do that. Yeah,
Yeah. Okay.
I can see
Okay.
that.
Sounds good. Okay.
Thank you.
So, I was asked to talk about deep tech innovations through access to uh, global experts. So I've kind of transformed the topic a little bit into talking about global collaborations. How do we innovate right here, right from here in India, on some of the most impactful problems through collaborations, right, with our colleagues um, and even external collaborators from academia. So I'll talk about three broad areas. One covering access to information in Indian languages. The second topic theme I'll pick is agriculture. And then as these large language models have become so popular and are being broadly deployed, uh, large also comes with this very huge computational cost, both not only at training time, but even when you're serving these models. So computational efficiency of these models has become a huge concern, right, for the industry. So I'll talk about some work that we have very recently done on efficiency of these large language models. So let's start with looking at, again, how do we provide access to information? And again, the motivation for this work is fairly obvious. As one of the previous speakers, Kalika, was also pointing out, often you have these technologies being developed, right, for the global north, and you find, again, for those of us who are the privileged ones, right, I would say maybe attending this conference, who can understand English, right? Life is good. We have all of these large language models, and prior to that, we've had kind of all of these capabilities from things like Google search and so on. Any problem you have, you can find kind of very high quality information on the web to get you started, right, on a solution to that problem, if you understand English. But again, if you don't understand English, things aren't as good. So one of the problems we wanted to look at was, how do we democratize that access to information, given that close to kind of 90% of our people in India are not necessarily very comfortable with English, and in most cases they would prefer content in their local language. So again, starting with this concept of masked language models that was developed in the first, like, original class of large models like BERT, where you mask out these words, certain percentage of the words, and you train a language model to predict those missing words. We started training it with a lot more Indian language data, and built this model called Mural, which at that time, a few years ago, it had the largest coverage at that time of Indian languages, 16 Indian languages plus English. And we found that, again, we were able to, on a whole range of natural language processing benchmarks, uh, ranging from named entity recognition to part of speech tagging to question answering, we were able to significantly improve the accuracy of this model, relative to the original model that would do very well on languages like English, but not so well on Indian languages, and in particular, very significant gains for transliterated text. And we incorporated this into, we both kind of made this model freely available on TensorFlow Hub and also Hugging Face, and we utilize this model in our own products like the Google Assistant, which uh, supports 8 Indian languages in addition to English. And what I've shown here are examples that if you are, let's say, setting an alarm in different, there are so many different ways in which you could say, oh, set an alarm for whatever, for me at 4 o'clock or 6 o'clock and so on. And all of these different ways in which people might express in their native language, we were now able to understand the user intent um, uh, as a result of this model. Uh, and then what we did was to kind of raise our ambitions further and said that initially, actually, I challenged the team, can you handle all 22 scheduled languages of India? And the team went further and said that, look, there are 60 languages in India that are spoken by over a million speakers, and there are 125 languages that are spoken by over 1 lakh speakers. So they took this attitude that if a language is spoken by at least 1 lakh speakers in India, we want that language understood and represented, better represented in our model. So that led to this effort called Morni, uh, which is an attempt to build the best multimodal representations for over 100 Indian languages. And one of the issues that we recognized as part of that challenge is in India, uh, there's a saying, "Kos kos pe badle pani, char kos par vani," that every few kilometers, uh, the language that we are speaking actually is changing. Even though we may formally call it, let's say, Hindi, there are, if you look at the way Hindi is spoken in Haryana versus Bihar versus UP, there's a lot of variation. So what we wanted to do was capture all of those variations across the entire country, which led us to launch this project called Vani in collaboration with Indian Institute of Science, and we have, which is proceeding in 3 phases. In the first phase, we have already collected data from uh, roughly 85 districts and made all of that speech data, about 15,000 hours of speech data so far in a variety of languages, and we have made that freely available. Over the next 2 phases, our goal is to collect data from each and every one of the 773 districts in India so that we capture the full diversity of how we speak. Uh, and and now what we are doing is we are taking some of these kind of capabilities, some of these data sets that we are building for with rich representations of Indian languages, and we are combining them with the largest and most capable global models that our colleagues have been building. So within Google, again, externally, this is known as the Palm 2 model, the most capable large language model. Uh, we took that, and what we have created is a variant of that model, which will have much better representations for these close to 100 Indian languages. And in fact, we have applied that recipe not just for Indian languages, but for many other underrepresented languages in the world, and supporting close to like over 1,000 languages in this new variant. And what we are trying to do is combine some of these large, like reasoning and other powerful capabilities of these large language models with much better representation in these other models of Indian and other uh, uh, languages with much lower representation. Very quickly, I know kind of we don't have much time. We took another area, agriculture, where again, which has been relatively less touched, where again, farmers who are a very important kind of, in some sense, stakeholders, they have and they do such amazing, provide such amazing service in the form of providing us food, and yet again they have been relatively untouched by or much less touched by advances in technology. So there again, the way we used, in fact, global collaboration is we were amazed by the number of our colleagues based outside India who volunteered 20% of their time. So Google has this initiative where people can volunteer for 20% of their time on any project of their liking, and we were able to get uh, dozens of our colleagues from outside India uh, volunteering because of the cause that they all were so excited about, helping improve the lives of farmers. In particular, we were initially looking at problems like identifying farm boundaries, identifying the crop being grown, estimating the yield, so that we are able to unlock use cases like providing farmers access to loans from banks instead of being at the mercy of these loan sharks who charge really outrageous rates of interest, or getting them access to crop insurance. And what we have been doing is, again, applying these AI methods by uh, analyzing satellite imagery. And through that, we have come up with the first such model, which is able to, for the entire country, which is able to identify these boundaries of farms, identify sources of water bodies, trees, and so on. And we've been piloting this in states like Maharashtra, Telangana, and in fact, making the solution available to startups in India. And there are startups like Teamup in Telangana, which have integrated their solution with this uh, landscape understanding capabilities that we have provided, so that they are now able to kind of uh, make their solution show a field wise view. And the goal is to then unlock some of these uh, use cases that will ultimately both benefit farmers as well as other players in the ecosystem. And finally, I know we are kind of almost out of time. Uh, the As we go to these large models, which have now hundreds of billions of parameters, needless to say, these are extremely expensive, not just to train but also to run. And one of the things that you would have seen in many of these releases as that you'll see these discrete size models. Oh, there's a large model for, let's say, llama, and a medium size model and a small size model, and so on. So we are still talking about often like 4 or 5 different sizes of these large language models. So the question we asked was, could you design a universal model with hundreds of sizes, ranging from the largest model that you're training to much smaller models that you may want to maybe run on device, or you may prefer, let's say, certain intermediate sizes for better trade-off in terms of uh, cost of serving and the power of these models, and which has led to this work on something called Matformer, which is building upon this idea of Matryoshka representation learning that our team. So this has been a global collaboration led by one of our researchers, Pratik Jain, with one of our student researchers who's at University of Washington, and with academic collaborators from University of Washington as well as a few other schools. And the idea there is to, instead of kind of this, so when you train, let's say, a model like this, think of this yellow colored model, which you might view it as the extra large size model. Can you again also, right at the same time, train a smaller model, the one in blue, which is large level, uh, one in, let's say, this orange, labeled medium, or the one in red, labeled small. So a given layer, you can jointly train, let's say, 4 such models. And as you have multiple such kind of layers, and as you pick and choose different sized blocks, you can actually get exponentially large variations in terms of overall different sizes of these models and their kind of correspondingly the computational cost and power. And what we've been able to show by doing this not just for vision models but also large language models is that we are able to, just by training a model once, we are able to get all of these different variants which are shown here in the star color with almost the same power as the original separately trained model for that particular size. And when you train these models separately, often you are limited in how many models you will be able to train. You are maybe limited to three or four such sizes. And now you can get hundreds and in fact even thousands of such variants. And what we have seen here, it looks large, but it's a very, very small overhead that you pay. And to me, this is analogous to the overhead that you may pay for virtualization. But once you have enabled that, just like virtualization enabled elastic computing in cloud, our view is that this can really enable elasticity in machine learning models being deployed, which can ultimately lead to very significant improvements in efficiency and in the cost. Uh, uh, because if you direct a simple query to a very small size model, which is good enough for that simple query, and only reserve the large models for the more complex queries, you can get pretty significant system level benefits uh, in terms of computational cost. Uh, so so with that, let me conclude that especially with AI impacting every industry and the rise of foundation models, in particular the large language models, we see a major disruption underway in this field of AI, which is leading to some very, very fascinating new problems as well as opportunities to develop solutions to bring benefits to billions of new people that the original developers of large language models perhaps weren't directly targeting, and again, some amazing opportunities for impact.
Thank you, Manish. That was pretty exciting and touching some of the key areas when it comes to India in terms of multilingual or languages, agriculture, and then the large language model. Very, very apt topics when it comes to India, actually. Thanks for sharing these interesting insights and giving us walkthrough of the some of the work which is happening within Google, actually, in a collaborative manner. Thank you very much, and